Hi, my name is Basir. In this video, we will be discussing what simple harmonic motion is, and then we'll also prove that the motion of a point projection of a particle performing uniform circular motion on any diameter is simple harmonic. Let us first discuss what is a simple harmonic motion. Let us say I have a rigid support here, and then we have suspended a pendulum from this rigid support. A rigid support is nothing but a fixed support which doesn't really move. Now, we have suspended a pendulum from this rigid support, and when we displace the pendulum, when we move the pendulum from here to this position, you would obviously know that the pendulum will try to move back in this direction. It goes back till here, let's say, and then it starts coming back once again. So this position that you see here, this is known as the mean position. You call it as the mean position, or you call it as the rest position, or you call it as equilibrium position, because when the pendulum is at rest, when it is not moving, it obviously comes in this position. Now this is known as the mean position. So when you displace a bob, let's say this is a bob here, and when you displace the bob actually goes to and fro about the mean position. The bob, it goes to and fro about the mean position. This is the mean position, or the rest position, or the equilibrium position, because when the pendulum is not moving, obviously it comes to rest at this position. Now you would have played, you would have used the swing at some point in your childhood. When you pull the swing to a greater distance and then you leave it, it moves with a greater speed, isn't it? When let's say this is the swing, and then you move it only till this far and then you leave it, it goes a little bit slowly. But then if you move it a farther distance and you leave it, it moves with a greater speed. So we see for yourself, the acceleration here is directly proportional to the displacement. The more you displace, the more faster it gets, right? So the acceleration here is directly proportional to the displacement. Let us say I'm denoting the displacement by x here. Now you are displacing the swing in this direction, but then when you leave the swing, it moves in the forward direction. You are moving it in the backward direction, but when you leave it, it moves in the forward direction. So the direction of the swing is obviously in the opposite direction, so we can write a negative sign to just so, because it is because it is in the opposite direction, we can write a negative sign here. So acceleration is directly proportional to the negative of displacement. So a simple harmonic motion is pretty simple. The motion is to and fro about the mean position, and the acceleration is directly proportional to the negative of displacement. Let us first discuss the definition of simple harmonic motion. A body is said to be in simple harmonic motion if it moves to and fro along a straight line about its mean position, and that's what is happening here. The bob is moving to and fro about the mean position, and the acceleration is directly proportional to its displacement, but in opposite direction, and it is always obviously directed towards the mean position. If you move it here, it tries going back to the mean position, and then it swings to this side, and then it again goes back to the mean position. It again tries to go back to the mean position. So the direction is always directed towards the mean position. If A is the acceleration of the body at any given displacement y from the mean position, then obviously the body is said to be in simple harmonic motion if the acceleration is directly proportional to negative of the displacement. Here we are denoting the displacement by y. And as you know it, if you remove the proportionality sign and if we keep the equal to sign, we have to use a proportionality constant. Here k is the proportionality constant. Okay, let's start discussing the motion of a point projection of a particle performing uniform circular motion. Now let us say I have a particle here. Let's say I have a particle here at time t is equal to 0, which means it has not started performing the uniform circular motion yet. When the time is 0, let us say the particle is at this point. Then the projection of this particle with respect to the diameter y dash is going to be this point which we denoted by 0. And if the particle, let's say it comes here, then the projection is going to be at this point. If it comes here, the projection is going to be at this point. If it comes here, obviously the projection is going to be this point. If it comes here, the projection of this particle on the y dash diameter is going to be at this point. If the particle comes here, the projection of the particle on the diameter y dash is going to be at this point. And if the particle comes here, the projection is going to be here itself. So the particle is moving in this direction. Let us say at time t is equal to 0, which means the starting time, the particle has not yet started its uniform circular motion. It was at this point and then it started moving in this direction. Let's say it started moving along this direction. And when it comes here, you would see the projection would be at this point. When it comes here, the projection would be at this point. When it comes here, the projection would be at this point. When it comes here, the projection would be at this point. When it comes here, the projection would be at this point. So you can see that the projection of the particle in the upper semicircle is going to be from this point to this point. And then when the particle starts moving along the below semicircle, the projection obviously moves from this point to this point. So you can see for yourself, let's say that is our mean position here, and the particle moves there in the to and then fro in this direction, to and fro about the mean position 0. So the particle starts moving to and fro about the mean position. Now we are supposed to prove that the motion of a point projection of a particle performing uniform circular motion on any diameter is simple harmonic. And what is a uniform circular motion? You would obviously understand a circular motion, right? The particle is moving along the circumference of a circle. And what do you mean by uniform circular motion? Uniform circular motion means it is moving along a circumference of a circle with uniform velocity, which means it covers equal distances in equal intervals of time. Let us say the particle is moving along with a uniform velocity which we denoted by omega, and let us say the particle at time t is equal to 0. During its starting stage it was at this point, and after some time t, let us say the particle moved to this point. Let us name this as P, and let us take the projection of this particle P along the diameter y dash. Let us say the projection on y dash of the point P is some capital N, and let me also try to draw a line here, and then let's say this line meets the diameter xx dash at some point N. I'm just trying to complete a triangle here. And let us say the angular displacement here is theta. Theta is the angular displacement. Let me write it for you. Angular displacement. Let us say the angular displacement is theta here. Then obviously theta is going to be omega t. And what is omega here? Omega is the angular velocity, right? The angular velocity here is omega. How did I come to this conclusion? Theta is equal to omega t. You must have studied in your previous classes. The velocity is the rate of change of displacement, right? The velocity is displacement by time, isn't it? Here the velocity, in place of velocity we are going to consider angular velocity, because obviously the particle is making a circular motion. It is moving along the circumference of a circle. So instead of taking the velocity, I'm taking angular velocity. The displacement here is the angular displacement theta, and the time, let me write it as t itself. So t is dividing on the right hand side, so it will obviously multiply on the left hand side. Omega t is equal to theta. So the angular displacement theta is omega t. So that's the reason in place of theta, let us write omega t here. And let us say that when the point was here and at the initial position, and then it moved from here to here, the projection of the particle, it moves from O to N, right? Let us say this is just some O. it moves from O to N, and let's say the displacement here we denote it by y. And let me take this as some m, because obviously we use the letter n already, so let us say this is some m. Now I would like to apply sine of, I would like to find out the sine of this angle here. And what is sine theta going to be? You know that sine theta is the opposite side by the hypotenuse, isn't it? The opposite side here is Pm by the hypotenuse here is the radius of the circle. The radius of the circle, we are denoting it by capital A here. So sine theta should be the opposite side by the hypotenuse, isn't it? The opposite side is Pm and the hypotenuse is OP. So sine theta is going to be, what is Pm? See, Pm should be equal to On itself. So Pm that you see here, it should be equal to y. So in place of Pm, let me write y here. Now OP, what is OP? OP is A here. So y is equal to A sine theta. And what is theta here? Theta is omega t. So let me write omega t in place of theta. Theta is omega t. So we see that the displacement should be A sine omega t. But I want to prove that the projection of the particle moving in a uniform circular motion on any diameter is simple harmonic. If I want to show that the motion of a particle along the circumference of a circle moving in a uniform circular motion is simple harmonic, then I need to show that the acceleration is directly proportional to the negative of the displacement, isn't it? Now this is the displacement. I want to find out the acceleration. How am I going to find the acceleration? Now you know for yourself that the acceleration is rate of change of velocity, isn't it? Acceleration is rate of change of velocity. But then what is velocity? Velocity is rate of change of displacement, isn't it? So now we have y as the displacement. If we find out the rate of change of displacement, we end up getting velocity, and then if we find out the rate of change of velocity, we end up getting acceleration. And that is what I want to get to at last, isn't it? So let's consider this. Let us consider this. Y is equal to A sine omega t, and let me start differentiating this on both sides, differentiating with respect to t on both sides, with respect to t on both sides. Now I'm differentiating with respect to t. When you differentiate with respect to t, you write t here, d by dt, that shows that you're differentiating with respect to t. So I'm differentiating the left hand side y with respect to t, and I'm differentiating the right hand side also with respect to t. And what is my right hand side? A sine omega t. Now a is the radius of the circle, right? The radius of a circle, it obviously is constant, it never changes. The constant, we will take it out of the differential here. So dy by dt is going to be a, which is the radius, is a constant, so I took it out of the differential and I'm left with only sine omega t inside the differential, right? Now what is d by dt of sine omega t? You know that d by dx of sine x is cos x, isn't it? So let me write d by dx of sine omega t as cos omega t. And then as per the chain rule, we have to differentiate omega t as well. So d by dt of omega t. What is that going to be? Let's move on to a different page here. D by dt is equal to, what is remaining here? A cos omega t. A cos omega t, and then I have to differentiate omega t. Omega, what is omega? Omega is angular velocity, and then since the particle is moving in a uniform circular motion, the angular velocity is constant, right? It doesn't change. So the constant omega, let me take it out of the differential, and then I'm only left with t inside the differential. And you know, as a matter of fact, you know for a fact that t, if you differentiate with t, you end up getting 1, isn't it? You must be aware of this. D by dx of x is 1. So x when you differentiate it with x, you get 1. T when you differentiate it with t, you end up getting 1, isn't it? Everything else, let me write as it is for now. D by dt, that gives me 1. So now dy by dt is a omega cos omega t. And what is this thing? This is rate of change of displacement. Y is the displacement of the projection of this particle on the diameter y dash, isn't it? And you know that the rate of change of displacement is the velocity. That's the velocity. So we end up getting the velocity as a omega cos omega t. Now that's the equation for the velocity that we got here. We can actually change this a little bit here. You know for a fact that sine square x plus cos square x is 1, isn't it? That's a trigonometric identity. Now in place of x, let us say we have omega t here, so I'm going to replace the x here with omega t. So you would know for a fact that sine square omega t plus cos square omega t is 1, isn't it? Now what is cos square omega t going to be? Plus sine square omega t. If I transpose it to the right hand side, it becomes minus sine square omega t, and then what happens? Cos square omega t is 1 minus sine square omega t. If I transpose the square from the left hand side to the right hand side, I end up getting a square root here. Then what is cos omega t going to be? It is going to be square root of 1 minus, what is sine omega t here? You can see for yourself, sine omega t should be y by a, isn't it? From this equation, sine omega t should be y by a. A is multiplying on the left hand side, so it should be dividing on the right hand side. So in place of sine omega t, let me write y by a. Let me write y by a here in place of sine omega t. The square, I'm writing it as it is. So what is cos omega t going to be? Cos omega t is going to be 1 minus y square by a square. And let me just do a simple cross multiplication here. A square into 1 is a square by a square. A square multiplies and then it divides completely. Now the root, let me distribute the root to the numerator, and then let me also distribute the root to the denominator. When I distribute the root to the denominator, the square and square root cancels, and I end up getting cos omega t as a square, square root of a square minus y square by a. So now in place of cos omega t, let me replace cos omega t with this thing. Let me write it once again here. Cos omega t, I'm going to replace it with square root of a square minus y square by a. Now this a from the numerator and then this a from the denominator, they cancel out, and then the velocity, we end up getting it as omega square root a square minus y square. So that's the velocity that we see here. But what is my aim? I want to find the acceleration. I want to show that the acceleration is directly proportional to the negative of displacement. To find out acceleration, what are we going to do? We are going to find out rate of change of velocity, because rate of change of velocity is the acceleration here, isn't it? Now the acceleration, let me denote the acceleration by alpha here. The rate of change of velocity, that gives you the acceleration, isn't it? Now velocity, what is the velocity? The velocity here is a omega cos omega t. So let me write it as it is, a omega cos omega t. And how do you differentiate a omega cos omega t? Now you know that a is the radius of this circle. The radius of a circle is always constant, it doesn't change. So a is a constant and omega is the angular velocity, and since the particle is making a uniform circular motion, the angular velocity remains same, so it is also a constant. So let me take the constants out of the differential. I'm going to take the constants out of the differential, and then I'm left to differentiate just cos omega t. Now you know that d by dx of cos x is nothing but minus sine x, isn't it? D by dx of cos omega t is going to be minus sine omega t, and as per the chain rule, you are supposed to differentiate omega t as well. And you know that when you differentiate omega t, with respect to t, you obviously end up getting omega, because omega is a constant. I'll take it out of the differential. When you differentiate t with t, you end up getting 1, so omega into 1 is omega. So we end up getting the angular acceleration as minus a omega into omega is omega square sine omega t. Now, in place of a sine omega t, I can replace a sine omega t with the letter y. I can replace a sine omega t with the letter y, where y is the displacement of this point, projection of this particle along the diameter y dash, isn't it? Now, you know for a fact that omega is the angular velocity, and since the particle is moving in a uniform circular motion, the angular velocity should be constant. So this is, my friend, a constant here, isn't it? Now if you remove the constant, you can obviously keep a proportionality sign here. So alpha is proportional to minus y. So we ended up proving that the angular acceleration is directly proportional to negative of the displacement. That is how we can prove that the point projection of a particle making a uniform circular motion, performing a uniform circular motion on any diameter, is simple harmonic. I believe you understood this. If you haven't understood this, I would suggest you to watch it a couple of times. I tried going as slow as possible because I wanted you guys to just make sense of everything that I said in this video. In case you have any questions and concerns, please feel free to let me know in the comment section. I look forward to see you all in the next video. Until then, goodbye.